Welcome to this session. This session is about the Arrhenius equation. Some people say Arrhenius, but you're going to hear me say Arrhenius over and over again. Hope I'm not tainting you for life. Arrhenius is the same guy that was the acid guy with the acid theory, and more importantly, he actually cared about the energy of chemical reactions, and so we tie him to his equation that helps us calculate the activation energy for any reaction, which is that thing that has been a bit ethereal for you for the last couple of years. We look at diagrams like this, where we have energy progress, or time, as appropriate in a kinetics chapter. And this is energy, and we talk about the energy at which these reactants began, and the energy at which these products finally end. And then we talk about the fact that the energy barrier that must be overcome for the reaction to occur at all is the activation energy. So you'll see me use the symbol E sub A. It's fairly universal, but there are other symbols, I'm sure, by other authors elsewhere, because, you know, you've heard my grown-ups can't get a long speech over and over again already. So we're going to go through the very final part of the kinetics chapter. Yippee skippy, happy dance, happy dance. Congratulations for making it this far. And let's dive in. So this is titled AP Chemistry, Arrhenius Made Easy, or at least as easy as it's ever going to get. What happened was, a while back, it's been, I guess, since 2007 maybe a little earlier than that, Arrhenius came back onto the test after a very long absence. And unfortunately, not everyone got that memo. So it's been really difficult for teachers and students alike to embrace the fact that this is back on the exam. It's actually very easy, especially in the land of the graphing calculator. And so if you've been following along and doing well with the integrated rate law stuff on the graphing calculator, this is just more of the same, only not as many lists required. So at the beginning, chemistry is defined as the study of matter and energy. You'd be amazed at how many kids I ask that, and they don't know the definition of that on a Saturday morning. So unfortunately, the study of matter consumes most of our class time because it's easier, it's tangible. We can measure it with a balance, or we can use a probe to measure things, or some other simple device. But you can observe matter directly in the case of liquids or solids, or at least observe its effects in the cases of gases, color changes, etc., bubbles forming. But you can also easily observe changes in matter as chemical reactions take place. The study of energy, on the other hand, is far more elusive. It's very challenging since only the effects of energy changes. Energy changes. Nobody has an energyometer. The energy changes can be measured. So consequently, two sets of measurements have to be made, final and initial, and calculations are sure to follow. So how do we know, we being the grown-ups, know that matter dominates the AP Chemistry classroom? Well, it's simple. I was a scorer of AP Chemistry exams for many, many years, and at the reading, year after year after year, students do a fine job of explaining changes in matter, but rarely can wrap their head around, or more importantly, their vocabulary around, the changes in matter to the changes in energy. And so valuable points are lost on the free response. And I don't want that to happen to you. I want you to get rewarded because you have the guts and the fortitude to endure these recordings. So students don't realize that the changes in matter are a direct result of the changes in energy, and it's a cause and effect relationship. You're more comfortable just dwelling on the effect and neglecting the cause. So this topic within the kinetics unit focuses on the cause, and that cause is an energy cause. So additionally, it provides the essential link between the study of kinetics and the study of thermodynamics. So quick review of the collision model, because I'm guessing you've listened to the earlier parts of the chapter on this. If not, this is your chance. If so, happily fast forward. So what we know so far is that the rate of a chemical reaction depends on the concentration of the reactants, that the order, which is that exponent in the rate law, of each reactant depends on the detailed reaction mechanism, that the temperature of the reaction affects the value of the rate constant. It's the only thing that affects the value of the rate constant. And a general rule of thumb regarding temperature is a 10 degrees Celsius increase doubles the rate. There are some parameters on that, but that's a general rule of thumb. The molecules must collide in order to react, but that's not all. They must collide with sufficient energy and the correct orientation or geometry so that the collisions are what we call effective. These big people words are what you want to put into your writing. So what else do we need to know? Well, we need to know why the relationship between an increase in temperature and an increase in rate is not a direct relationship. Why thermodynamically spontaneous reactions, such as the combustion reactions or the conversion of carbon graphite to carbon diamond don't just happen spontaneously. And why the activation energy is so very, very important to both kinetics and thermodynamics and this little field of study called biology. So, I think you say Svante, but again, I've got a Texas twang that can butcher any name on the planet. So, in the 1880s, Arrhenius, the acid guy, first proposed the existence of some threshold energy, and he called it the activation energy. Thank God he had some good sense, and he called it something that made sense. Activate the process, you got to overcome the activation energy. So that's got to be overcome to produce that reaction. So the collision model is simple. The kinetic energy of the molecules before the collision is converted to the potential energy as the molecules are distorted during the collision to break bonds and rearrange the atoms into the product molecules. And I remind you yet again, it takes energy to break bonds. Energy is required to break bonds. Energy is released when bonds are formed. So you've seen these diagrams a gazillion times at this point. Consider this reaction. So we have 2 BrNO yields 2NO and a Br2 in the gaseous phase. So everybody's in the gaseous phase. So not a big giant change in energy, and we also call that a delta H sometimes, not just a delta E. But we see this activation energy this direction. I remind you that there is an activation energy for the reverse reaction, and it's larger. R for reverse, pretend that looks like an R, pretend you can see that. I think I can make this, maybe, can I make it one step bigger? Let's try. Oh, better, how about that? Still can't see that's an R, but there you can. Alright, so we envision this progress, reaction progress, as shown above. Never be surprised if the words transition state are replaced with activated complex or even intermediate, because those terms describe the highly unstable collection of atoms bound together at the top of that energy hump that can either drop down this way or this way, depending on what collision occurs with them next. So, likewise, reaction progress can be replaced with the word time, especially in a kinetics context. And activation energy, again, is that threshold energy that we have to overcome. You've known about it for a long time. This is not news to you. If you're asked to compare graphs of this shape, remember the taller the hump, the larger the activation energy, the smaller the value of the rate constant. The larger the activation energy, the smaller the value of the rate constant, and the slower the rate. Books don't exactly lay that out for you. That's just little old me explaining that to you. If you have a really high activation energy to overcome, then rate is equal to K, blah, 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 blah. That value is going to be small because this is going to be a slower reaction. All right, then delta E is that net energy change, and it's representing the enthalpy of the reaction. And so I ask you, is the above reaction exo or endo? Go ahead, I'll wait. Indeed, it is exo. How come? Because energy was lost. Value here compared to value here. There's the change. These are in a lower energy state. Therefore, energy was lost. And a lot of that energy is lost in the form of heat, so we would call it delta H, and we would give it a negative sign for the concept of being lost. So, how does temperature affect the activation energy? You need to be able to interpret graphs like this, and they're not that intuitive, so I'm going to walk you through it. Temperature is defined as the average kinetic energy of the molecules, right? Temperature is proportional to the kinetic energy average of the molecules. That is the definition for temperature. I watched a professor in graduate school make a whole room full of grown-ups cry over that concept. And all he wanted to, the answer to the question of what is temperature. He didn't want ethereal, oh, it's the amount of hot or cold and stuff. Bull. It is the average kinetic energy of the molecules. Fortunate for me, I knew that. I gave the answer. I was not crying. I wasn't instantly popular either among my peers, but I did know the answer. So the higher the temperature, the higher the average kinetic energy, the more energetic the molecules. Heat them up and speed them up. Think heat them up and speed them up. More energy, going to react faster. Heat them up, speed them up. So the more energetic the molecules, the more energetic the collisions, the faster this is going to go. So let's analyze this graph for a minute. We have energy on the x-axis, easy enough. We have number of collisions on the y-axis, easy enough. Which temperature is greater, T1 or T2? Which temperature has more molecules with enough energy to overcome the activation energy? All right, let's talk about the concept of area under the curve. When you see these curves like this, these are actually like bell-shaped curves, normal distributions, optimum type situations. So here is my activation energy threshold on that x-axis. So in the blue, everything right here represents the quantity of molecules with sufficient activation energy to get past that threshold energy. That's not all of them, is it? Because under the red one, there's way, way more. So under the red one, we get all of this. So what does that mean? That means that T2 is higher and T1 is lower. Kind of counterintuitive, huh? Because you're seeing that big hump and you're thinking, well, T1's got a big old hump, so it's got to be higher. No, 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 no. So T2 is greater temperature, higher temperature. Why? More molecules have sufficient activation energy to react. So which temperature has more molecules with enough? That would also be T2. So be able to talk about the why. More molecules have achieved the threshold activation energy and go on to react. This is just another artist's rendition of the same exact concept. I want you to see it in different ways so that it doesn't throw you if you see it on the AP exam. So generally, when the temperature is doubled, the fraction of molecules having high enough energy to overcome the activation energy way more than doubles, which explains why the relationship between reaction rate and temperature is not linear. It's actually exponential. And I know you need proof because you don't trust me, but it's just your lack of faith is disturbing, to quote Darth Vader. If we graph the value of the rate constant K versus the Kelvin temperature, we do not get a straight line, do we? No, we do not. We get a curve. And that curve is not linear, but rather it is exponential, meaning that the natural log function is in your immediate future yet again. If you double the Kelvin temperature, you more than double the rate constant. Since calculus, again, is not a prerequisite for this course, we're going to linearize the data. Y equals mx plus b is your friend. Slope is your friend. This has been something you have embraced since middle school. So I hope you're getting your mileage out of it. And I hope you've written a letter of thanks to the person who taught you about slope and y equals mx plus b in the first place. Sometimes you got to pay it forward. All right, so Arrhenius derived the following equation, which is way too complicated and very frightening, but let me decode it for you. There's something you know, rate constant. Here's something you know, activation energy. Ignore the minus sign for the moment. Hey, there's R. This must be the energy R, though, since we're talking about activation energy. So this is the 8.31 joules per mole Kelvin, R. And this temperature here is obviously in Kelvin. They gave us a little K there to remind us of that. So it's this stuff right here that's annoying. So the constant P is the fraction of collisions with proper orientation for reaction. Okay, so that's the orientation factor. Then this is the constant related to collision frequency, how often these molecules collide. And then we've got one that is for the sufficient energy, enough oomph as they collide to actually make or break bonds. So we just lump all of that together and we made a new constant. And that constant, go ahead and guess. What letter would we give it? Give you some hints. What do you think? Indeed, A for Arrhenius. So relax. You don't have to worry about that. It's just my obligation to educate you on where all this stuff comes from. So that's kind of scary. But I'll spare you the derivations that allow us to arrive at the one that you do need to know. You do need to know that we're going to put the natural log of K values. Those are the same sweet K values that you could find with algebra if you were doing differential rate law, which had concentration rate data in the table logic or ugly algebra approach stuff. You know, you've been doing it. You didn't start here. Or integrated rate law with your calculator and the graphs, making the graphs to determine zero, first, or second order, the slope of which absolute value of the slope to be more exact, of those graphs with the highest R value for the highest linear fit, best linear fit, is going to be your K value. So take the natural log of K's, which means you have to do this at different temperatures, because the K is constant at constant temperature, so you got to repeat experiments at different temperatures. That is equal to the negative, and it's because in the graph you're about to see the slope is negative, so we got to get rid of that negative sign, so we toss a negative onto this equation. The negative activation energy divided by R is the slope. We're going to graph on the x-axis reciprocal Kelvin temperatures, reciprocal Kelvin temperatures. Can you feel some temperature conversions? A lot of adding 273 coming in your future. And then we're not really worried about this term, but this graph is not going to start off at the origin, so it's going to have a y-intercept that is not 0, and that value is equal to the natural log of A. I've never seen a question where anyone has asked you to then solve for A by looking at the y-intercept and taking the inverse natural log of it, but you never know. So what this does is it allows us to simplify the relationship into our good buddy y equals mx plus b. See? Y equals mx plus b. And that is going to, like I said, A, that constant is replacing P and Z in the original equation, and you're going to be asked to solve for rate constants, activation energies, or temperatures. So here's the graph that we want to learn to construct swiftly, quickly, efficiently, expertly. Natural log of K's versus 1 over Kelvin temperature. Understanding that the slope has meaning, that the activation energy can be computed by taking the negative energy R times the slope. So you know that activation energies have to be positive, right? Think about this. There's that graph again. This is energy added to system. So they're definitely not negative. Activation energy is definitely not being released. It's the energy you need to get over that hump. Now you can do your little algebra thing as well if you're an algebra aficionado. And if you prefer algebra methods over graphical methods, go for it. I know me. I make algebra mistakes. I like the graphing calculator. It cuts down on my mistakes. So that's the direction I'm going to take you. But you certainly can stop listening to me at any point. I'll never know the difference. Now at this point, I give you a full graphing calculator tutorial, not intended to insult your intelligence, but you people lose things. You misplace things. So this is just the quick and dirty. Here's how you enter data into lists. Here's how you perform a batch transformation. Here's how you run a linear regression and graph the data. Here's how you determine y when given x. Here's how you determine x when given y. This is all on the handout that is on the wiki page. Now, we're gonna move from this piece of your handout that was on the wiki page or given to you by your teacher, whichever, into the actual problems. And here comes a calculator. You knew it was coming sooner or later, right? So let me get this set. This is too big. Bear with me. All right. Since this was a panic mode a few years back when this first came onto the exam, the textbooks didn't have a whole lot of practice problems on this, so I had to go mining for problems. And so at the top you'll see that all of these came from different authors, different books. This one's from Zoomed-Off 5th edition, and I adapted it. I asked some more thoughtful questions than what the authors ask. Not that they do a bad job, but sometimes they don't get the big picture. That's why I'm not a fan of the problems in the back of the chapter. I learned after a few years of teaching AP Chemistry they were not preparing my students well, so I went to an electronic system that gave me back data on drill and skill called the UT homework system, but it could be WebAssign, it could be whatever. I just hope you're doing electronic homework somewhere, somehow. And then I wanted to make sure that you understood this conceptually as well, because textbooks, again, get a little too wrapped up in the calculation, not so much in the concept. So those are my disclaimers for stealing from books, but crediting my source, so I think that keeps me out of trouble. So experimental values for the temperature dependence of the rate constant for the gas phase reaction are as follows. Pay attention to the headings. I have Ks and I have Kelvins. So that's cool. That means I'm in the land of Arrhenius, if you didn't already know that. So pay attention to the headings. If they give you K values, notice they have to be at different temperatures because K depends on temperature. If you want a different K value, you've got to use a different temperature for your reaction. Off we go. Show all work and pay particular attention to sig figs and units when reporting your answers. Is this reaction fast or slow? Think about it. Think about it. Rate equals K concentration in O to some power, concentration O3 to some power. Look at the size of those Ks. Oh my God. They're on the order of a billion. That's pretty dang big. Look at those temperatures. These are Kelvin temperatures, y'all. 0, see I managed to get a y'all in there. 0 degrees Celsius. 0 degrees Celsius is 273 Kelvin. This is room temperature at 25 degrees. These are cold. All of these are less than room temperature. So at low temperature, we still have incredibly fast reactions. So this is one fast puppy. Fast. Justify your answer. Since, I want you to justify it two ways, by temperature and by K. In other words, I want you to use all the data that they've given you. Since at fairly low temperatures, K values are extremely large. I would even say the word huge is in order. And then, from looking at just the data in the table, what is the overall order of this reaction? And justify your answer. I'll give you a couple minutes to think about it. You may even want to pause me. Think, think, think. Temperature doesn't help me with that. Would K help me with that? What about K would help me with that? Those pesky units on K. Let's contemplate the pesky units on K for just a moment. Liter over mole is the same as a number for K, molarity in the bottom, and seconds in the bottom. So if you've been doing what I've been asking you to do and thinking about the overall order of a reaction, then you've been putting up fingers, which makes you feel foolish at first until you get the hang of it, putting up fingers for the overall order. And then you've been dropping a finger to put the right number of molarities in the denominator of your K values number. Now go backwards. There's one molarity in the denominator, so put up a finger for the one, and now put up the finger you would have normally dropped. And bingo, you have two fingers in the air, so it is second order overall. As indicated by examining the units on the K value. Now the fun begins. What is the activation energy for this reaction? This is where we must graph. What are we graphing? Let's recap. Ln of K and 1 over Kelvin temperature. All right, so 1 over kelvins. So we have temperature and we have Ks. I like the temperature since it's going to be on my x-axis. I like to put it in L1 the way I like to put time in L1 because it's on my x-axis. And so this will be L2. So this one started off kind of kind because it put them in the table in the order that I like. Don't always expect that. So I've cheated. I got a head start on you. So pause me and put all these numbers in. Make sure I get mine in there right. I think I have them all in there correctly. And don't be alarmed when you put these in. If they all get rounded to fit all that stuff on the screen. They're still holding what you put in. And let me give you one last hint if you hadn't started. You can, since these are all 10 to the minus 9, you can just type in this coefficient part all the way down, your L2, then go to the tippy top and transform it so that it all gets multiplied by the 10 to the 9th at the same time. So up at the tippy top of L2, you would type in L2 second EE, where is that? Second comma. Pretend that looks like a comma. That gets you to the EE command. 9. And enter. Because I'm way too lazy to type second EE9, second EE9, second EE9 over and over and over again. And I would even be willing to use my brain and change an exponent so that I didn't have to do that umpteen times. Okay, so hopefully you've restarted me and we are on the same situation here and we are now ready to graph this puppy. So what I have in here so far is Kelvin temperatures. What to do, what to do. They need to become reciprocals. So right there in the same column, I can say second L1, take the reciprocal. I love the reciprocal button, as you know. And now they're all reciprocals. And then I could come over here and I could say I need the natural logs of k's. These are all the k's. I just need to take the natural log, ln, of everything that's sitting in L2, and that'll paste it right back into L2. Voila. Now I need to do a graph, and I need to run the linear regression on it because what I really need is the slope, because activation energy is equal to minus r times slope. So I need the slope. I don't even really have to look at the graph, but these last two questions are going to force me to use the graph to calculate, or the algebraic equation if you prefer. I'm too lazy for that. I'm going to use the calculator. But I'm going to go ahead and set up my graph because I know I've got to have it sooner or later. The good news is it's not like integrated rate law where you have to keep changing your lists. We're pretty much going to stick with L1, L2. So go in there, leave it on scatter plot because you're big kids now. You can't use line connecting dots to draw pictures anymore. And zoom 9. I know, it always gives me that issue. But I haven't run a linear regression, which is why we have no line. So stat, calc, item 4. L1, L2 is the default. So I can put that in like we did with integrated, or I can just know that. And I just need it pasted into Y1. So alpha, trace, Y1. I'm on the new operating system, and you should be if you have an 84 or better. If you don't, then you get that Y1 by going vars, yvars, enter, enter, and enter one more time to actually make this happen. But I'm going to delete that and just press this. All right, so what we get is a nice correlation of 0.997, and then I'm after the slope. So it's going to equal, the activation energy being it's going to equal negative 8.31 joules per mole Kelvin. Notice the joule, that's the part that's important. Times this slope, which is in reciprocal kelvins. So I'm going to come out in joules per mole, because the k's are going to cancel out of this. And the slope is a negative 1435.7, and that's in a reciprocal Kelvin, so it's over kelvins as well. But just trust, I'm not going to clutter this up in this small space with a bunch of units. Okay, so now negative 8.31 times negative 1435.7 equals a big old giant number of 119.30, right? 11,931 to be exact. So what do we end up with here for an actual answer? Let's put it in kilojoules. That's going to be easier on us. So I go 1, 2, 3 and say 11.9 kilojoules. That's not pretty. Kilojoules per mole. Did I do that right? I believe so. Yep, 11.9 kilojoules per mole. We're good to go. All right, so now let the calculating on the graph begin. So get your graph. Because I did that linear regression, now it actually has that equation pasted in because I put it in Y1. What is the value of K when the temperature is blah, blah, blah? Okay, do not lose sight of what you graphed. First of all, is K an X or a Y? It's a Y. Is temperature an X or Y? It's an X. And so you know X and you seek Y. So you get to go second trace and the first item on the menu, when in doubt, choose it, and X equals pops on your screen. But does X equal 455? No. X equals the reciprocal of that. So it equals 455 to the minus 1, or 1 over 455 if you prefer. And then when I get Y, Y is going to equal ln of K, so I'll have to take the inverse natural log of that. So let's look at our table. we're looking at 455 Kelvin, so it's outside of our range. I'm expecting to have to zoom out. Matter of fact, I'm going to do that first. Zoom 3 for out. Nothing has happened yet. Oh, got to hit enter. Ah, nice ooched points. So I'm going to now go second trace on this graph. And it says x equals, yep, x equals 455. Take the reciprocal thereof. And y equals 24.9, but 24.9 would look really dumb in this table. Definitely doesn't fit. So, ha ha ha, think about it. Oh yeah, it's a natural log of it. So, second quit, second ln, get my e there, and alpha 1 to get the y, because it actually stores it as y. If you didn't hear me on the previous recording, I didn't know that for a very long time. I used to write down the number till finally one beautiful Saturday morning in Texas, a child raises their hand in the middle of a student study session and says, "Hey miss, did you know it stores that as y? You keep writing it down and typing it back in." Ah, I walked over and I gave that child chocolate because he made my life so much better. So I don't have to do that anymore. It's much faster. So enter, and I come out with 6.62 times 10 to the 10th. 6.62 times 10 to the 10th. You betcha. Heat that baby up, it's going to speed up. That K value increases, just the way it did with every time the temperature increased in the table. So that makes nice, perfect sense. So now you know we get to do it the other way, right? Now, what is the temperature? And you ask yourself, x or y value. Looking for an x. Also realizing that when you get x, it's going to be a reciprocal, right? It's going to be a reciprocal of Kelvin. And then the rate constant has a value of this, so I need to realize that's a y, and I need to put it in as a natural log of the value. So we're into the I know y, I seek x, so when you know y, use the y equals button and put it in. From past work, my natural log, don't clear out y1. You went to a lot of trouble to get that in there. That I want to clear. So ln of 2.25, second EE9. And I'm going to graph it. 2.25 second EE9 would be in here somewhere. So notice I would have had to zoom out for that. 22.5 times 10 to the 9. Fits somewhere in there between 12 and 35 and a half. So I'm expecting a temperature between 298 and 369. Hope I get it. Okay, so now all I need is that, I need that intersection. So I'm going to go second trace, intersect, and just keep hitting enter until the word intersection comes up on my screen. But when I get it, remember that x is equal to the reciprocal of what I really seek, which is the Kelvin temperature. So second trace, item 5 is intersect, enter, enter, enter. And y is 0.0055, which makes no sense. But then you realize, I need the intersection of that. So second quit, second quit right there. And my x is in front of, on top of my store button. So alpha, oh, you know what? I can do that faster. Have you ever used this button just to get to x? That gets you x too. Just that button right there. It says x right there. You just click it and then take the reciprocal of x. And I get something that makes more sense. X equals, or the temperature, I should say, T equals 200 and, let's make it 20. 220 Kelvin. Put a dot there and be 3 sig figs. Does that make sense? Not really. Why doesn't that make sense? It should have been a little higher than that. 22.5 times 10 to the 9th. Is that what I put in? No, I'm off by an order of magnitude with my silly typing. Let's try that again. See, that's a good thing to be putting it in there that way. 22.5. Delete. 0.5. Second insert 5. Let's try that again. Graph it. Intersection, clearly moved. Second. Trace. All kinds of struggles right now. 5. Enter, enter, enter. Now, quit this screen. Take x to the -1. Ah, that makes much more sense. 339 Kelvin. Yep, 339 Kelvin. So there's value in actually putting it back up in your table, because even I make lots of mistakes. Okay, so 1 down, 5 to go. Let's look at number 2. This one is adapted from an author, last name of Brady, and it was number 96 in the chapter. Imagine, why do you need 96 problems? Good grief. That's just torture. Okay, so now see these? Yeah, I got some -3s here. If you want to do that batch transform thing, I suggest you fix these to 12.6 and 19.4 so that those go to -4s, and then you can just type in all of that mess and then take it all to 10 to the -4, and then what else should we notice? Those are K's. What's in that other column? Those are temperatures. I like my temperature in L1. I like my K's in L2, so I label them that way so later I don't get confused, because I'm easily confused at my age. And then, yeah, they're trying to trick me. Look at that, degrees Celsius. What to do? Got to convert it to Kelvin and then take the reciprocal. Need Kelvin. Okay, so get busy typing. Clear all your lists. Second plus to get there. 4 is the command. Clear all your lists. So start typing. I'm going to recall because I've got them saved. Probably not doing what I'm doing. I do this so much I've already typed it all in. Okay. Pause me until you're ready. All right, you've got them in. You've double-checked your typing. Remember, I like my temperatures. You don't have to do it this way, but I like my temperatures over in L1. I make fewer mistakes if I just stay with this rhythm. And I like my K's in L2. And I need, first of all, to realize that even though these look like they're Kelvin because they're in the 300s, they were trying to trick me. So I need to add 273 to everything here. So second L1 plus 273. Do you want to put the 0.15 or do you just want to leave it? It's your call. We're not going to get terribly different answers either way, but we will get a little bit different. So I'm just going to leave it at 273. That's peachy. And now I need to also take the reciprocal of everything in L1. Could have done that in one step if you're wondering. Just didn't think to do it until it was too late. Okay, so now over here, what do I need? I need the natural logs of everything in L2. Ta-da! Okay, so what do they want to know first? Is this reaction fast or slow? Think about it. Well, those K values are kind of little, on the order of 10 to the -4. Those temperatures are kind of high. I certainly wouldn't want to be in a lab that was at 400 degrees Celsius. So I think it's slow, since at high Celsius temperature, the K values are relatively small. What is the activation energy for this reaction? So now we get to do our graphing business and yada, yada, yada. So if I graph this, I've still got my stuff in there from last time. That's what you know when it starts coming across. You don't see any dots or anything. So go clear out your y equals. Clear and clear. and go zoom 9 so that you get your graph fit perfectly. Very nice. Now let's run that linear regression. So stat, calc. Since I did everything, it's item 4 to get a lin-reg. I did everything in L1 and L2. It's going to default L1, L2. I can type it in if it makes you feel better, but all I really need to do is paste this into Y1. So alpha, trace, there's my Y1. And hit enter. I'm after the slope. So activation energy is equal to minus energy R times the slope, which is equal to minus 8.31 joules per mole Kelvin. My Kelvin's going to cancel here in a minute. And the slope is negative 9450. Let's make it 9460. So I'm going to come out with a positive value. You don't have to write that, but I'm just doing it for emphasis. So 8.31 times, I already gotten rid of my negative, so negative times a negative, you know it's going to be a positive, so just 9460. Sorry, I did that in my head. It's a dangerous head sometimes. Let's go with 78.6. 78.6 kilojoules per mole of reaction. Now, if you'd have added the 0.15, I think you really came out with 79.1, which I guess is what I did on the original key that I wrote. So close enough. We're still right there. We're agreeing on 79 kilojoules per mole to 2 sig figs, which is probably what I should be using since some of those temperatures are only in 2. So what is the value of K when the temperature is 640? What is the temperature when the rate constant has this value? So what are you seeking? Value of K, is that an X or a Y? That's a Y when you know X. And X is the reciprocal of that Kelvin temperature. Now, that's done in Kelvin on your sheet, so be careful. So, graph, should have my line there now, and it does. Would 640 Kelvin fall in your range? Maybe. Close. Let's see. So, second trace, I know what X is, so I just hit value. And I put in 640 and take its reciprocal. And there it is. Yep, it's within range. So that means that my Y is actually equal to the natural log of K. So therefore I need to take E to the negative 6.97 yada yada yada, but remember it's stored as Y. Therefore K equals. So get out of this. Get my natural log inverse action going, which I didn't. I didn't hit the key hard enough. There we go. And Y, alpha 1. There we go. 9.31 times 10 to the minus 4. Now 640 Celsius minus 273. Kelvin minus 273 would put them back in, so let's just call that minus 300. We're looking around 340-ish. So we're looking somewhere in that neighborhood. Does your answer for K make sense? 9.31 times 10 to the minus 4. It's on the order of minus 4, and it fits into the range. So you're looking at something in there. Again, I rounded high on that in my head business, so we're somewhere in between there. So that's good. We're good for that. What is the temperature when the rate constant has a value of? So here's my rate constant. So that's a Y, but it's going to equal the natural log of that K value. So come to your Y equals, because you know the Y. Leave that regression in there because you have to go get it back if you didn't. And take ln of 50.5. Try to type it right this time. Second EE minus 4. Graph it. If we have an intersection, we're good. If we don't, we zoom out. Zoom out. Zoom 3. Don't forget to hit enter. Please, intersection, please show up now. There we go. It cannot calculate what it cannot display. So second, trace, 5. Just pound that enter key until you see the word intersection. So there you go. So what does that mean? That means that I know Y, so I'm looking at a Kelvin reciprocal. 0.00138, yada yada, but remember it saves it as x. Quit this screen. X to the minus 1. Therefore, temperature equals 700, and I'm going to call it 3, 723 Kelvin. Does that make sense? 50.5 times 10 to the minus 4 is way outside our range. That's why we had to zoom out. And that comes out to be 723 Kelvin minus 273, 450, which looks even better in the table, degrees Celsius. So going back and looking at the table and using that technique is going to keep you out of some trouble. All right, so we've got 2 down. Onward to number 3. And again, if you already get the hang of this, why are you still listening to me? All right, so let's see what I can do to you on this one. I didn't do it to you, actually. The author Chang did it. Notice this one's only number 37 in that unit. They ordered this earlier, or didn't put 100 and some odd implements of torture in there, in that chapter. Okay, here's my balanced equation. Data given in the following table. I still like L1, I still like L2, and again I'm noticing those are degrees Celsius, so add 273 to the whole bloody mess. So I'm going to go get mine, you start typing. And again, you got -5s, -4s, and -3s. You decide. If it's this tricky, you may want to just go ahead and type them all with the second EE function. So you can be typing while I'm going and getting mine set up as well. All right, so all I did was put the data in. You can pause me if you're not caught up yet. That's the beauty of these recordings, huh? Doesn't even hurt my feelings. Okay, so let's fix our data. What's wrong? First of all, these temperatures are Celsius, so we need to make them Kelvin, and we need to take the reciprocal. You can do it all at one time if you want. You can say, open a paren, L1 plus 273, and you can add the 0.15 if you want. I'll add it this time. I didn't last time. Closed. Take the reciprocal of the whole bloody mess. Boom. There they all are. All right, and then over here, I need the natural log of everything in L2. Whoosh. All in at once. And we're good to go. So once again with this question, this general conceptual question, is this reaction fast or slow, and justify your answer. Well, those are low temperatures, and those are low on the order of 10 to the negatives K values. So this is mighty slow. Mighty slow. Since at low temperature, the K values are very small. What is the activation energy for this reaction? Well, that's my graphing moment. So zoom 9. There's my stuff I need to get rid of. So I'm going to come and get my natural log out of there. Clear that out. I'm going to run the regression. Stat. Calc. 4. And just paste it into Y1. And there we are. So the activation energy is equal to minus R, that's the energy R, times the slope, which is minus 8.31 joules per mole Kelvin. Kelvins are going to cancel here when I multiply by the slope. And that is a negative 12404. So negative 12404 times negative 8.31. You know it's going to be a positive answer anyway. That would be 103 kilojoules. of reaction, if we must. Okay. What number am I on? I'm on number 3. Make sure I got that right. Yep. Okay. Just checking my key, make sure I haven't done anything stupid. Okay, what is the value of K when the temperature is 100 degrees Celsius, which would be 373 Kelvin? I can do that in my head, but be sure to take the reciprocal of it. So you seek a Y value when you know an X value. Okay, so get that graph back on the screen. It's pretty. All right, so alpha trace. Phooey. Try that again. Graph. Alpha trace. Why do I keep doing that? Second quit. I don't even need to do that, do I? Alpha. Not alpha. That's the problem. Second trace. Duh. Okay. I'm getting lulled into a coma myself. You guys are bound to be tired. So, what do I know? I know an X value. So just hit this, and I've got 373, but take the reciprocal. What do you mean go to? What's the problem? Zoom 9 maybe? Or zoom out rather? Still got that weird line. I thought I got rid of that. Clear. Got something going on here. Okay, so, oh, that's just an axis. Okay, so let's go with looking back at my data. That's all correct. I know that's all correct because we got the right answer on that. All right, so zoom 9. I'm having technical difficulties. Zoom 9. Oops, I moved a point. Dadgummit. Okay, second enter. Second quit. Second enter. All my dinking around, I've messed something up. I have a giant mess on my hands now. Alright, second quit. Let's go back to the data. Because I messed up something there. Yeah, I messed up that first data point. Okay, I'm going to see what that was supposed to be. That was supposed to be negative 10.96. Sorry about that. Let me try that again. Graph. Zoom 9. Y equals. Clear that puppy out. Second quit. Stat. Calc. 4. Alpha. Trace. Y1. Thanks for your patience. I'm sure you're way ahead of me, which is quite alright. Okay, so there's my 12.406 now. Oh, because I probably truncated something about that log. But that's okay, it's going to be close enough. Now I'm back to the fact that I need to go to my graph. That's more like it. 100 degrees Celsius plus 273 is going to be 373, and I need the reciprocal of that. 373. This is where it went wrong last time. Let's see what happens this time. Why am I getting that number? $100 degrees Celsius is outside my range. Okay. Second quit. Zoom out. I know, y'all are way ahead of me, and it's okay. Sometimes it's good for you to see me goof up. I'll do it regularly for you. How about that? Second trace. Eighth time's a charm. How about that? Okay, so now I have a Y value, which is equal to the natural log of what I seek. So it stores it as y. I'm going to quit this screen, go second natural log, and then alpha 1. Lord, that was way more difficult than it needed to be, wasn't it? So now, does that number make sense in this table? If I wrote that in scientific notation, it would be 7.38 times 10 to the minus 2. So in context, yes, that is making sense. Then my value of K is increasing with increasing temperature, and the amounts look even fairly good. So now, what is the temperature? So what is X? Remembering that we've got reciprocal kelvins. And I probably should answer back in Celsius. If somebody asks you a question in English, you should respond in English. And there is my rate constant value, so I need the log of that, natural log of that, natural log of K. Try that again. ln of K. All right, so we go to y equals. We come down one, and we go ln of 9.65 times 10 to the minus 4. And there we have it. Graph it. Do you see the intersection? Yes. So you don't have to zoom out again, which is good. And so we want to know what the X temperature is, so we want that intersection. So second trace, 5. Pound that enter key until you get the word intersection on your screen. So now we know that is stored as X, and I just need its reciprocal. So second quit. Use that button to get my X. Get the reciprocal of it with the reciprocal button. Try that again. Yes. Enter. X equals temperature equals 329.97 Kelvin. So subtract 273.15 because I added those in that way in the beginning, and I got there. 56.8 degrees Celsius. 56.8 would fit right here, squished in there, and 9.65 times 10 to the minus 4 makes perfect sense with that.